Silver. Today we're going to be presenting to you our work on the in-situ manufacturing ceramic with embedded silver heat exchange device. So this is a general overview of what's going to be presented in this presentation. Some of these sections will have subsections and they will be expanded upon when we get there. So the problem statement is essentially we wanted to produce a heat exchanging device for long-term space exploration missions. What we wanted to use was the material from the site that the astronauts would go to produce the actual device. And we wanted this process to be highly repeatable so that way if they were in a hostile environment, they were able to produce it with minimal effort. So the motivation, as with most motivation in life, was cost. Right now it costs about $3,000 to ship a pound of material into space. In-situ resource utilization is a great way to reduce the weight and volume of those materials and ultimately the cost of shipping things in outer space. So with that, we found the application for the ceramic heat exchanger to be best fit for long-term space exploration missions. So now I'm going to hand the floor over to Sasha, who's going to go ahead and give you a little background on how the project was developed.
So an in-depth literature survey was conducted in order to better understanding of ceramic manufacturing. For that, we looked at sintering studies, mechanical properties of ceramics, and the interaction of materials at the microscale level. So in order to ensure that the structural integrity of the device was fine. Next, we looked at a tape casting process in order to understand the different components and better understand the techniques needed for creating the ceramic slurs. We also looked at different microchannel designs and the routing methods for LTCC. LTCC stands for low temperature coal-fired ceramics, and it's a proven mature technology, and it serves as the basis for the majority of our design decisions. We also looked at fluid mechanics and heat transfer, as it played an important role in designing this heat exchanger. It's mostly served as a review of topics covered in previous courses, and special attention was paid to microfluidics and heat exchangers. So for this project, there were three primary tasks. We had to create a microchannel heat exchanger using LTCC. For that, we chose DuPont's 951 LTCC tape. We also had to characterize the thermal impedance capabilities of both the LTCC and regolith-based devices. And lastly, we had to construct a regolith-based device that permitted fluid to flow without delaminating or failing due to erosion or corrosion. So for that, we were forced to test the tape. First, we had to cast a tape using mostly composed of this lunar regolith simulant. And then we had to design the micro heat exchanger in such a way that the top layer would serve as a staging platform for heated elements. We were then to construct a heat exchanger of both microchannel devices using both LTCC and regolith. And lastly, we had to test the operation capabilities of both devices to verify our engineering analysis. So the construction process begins with stacking and laminating ceramic tapes using a heated manual press. We then drill microchannels and pins in through the surface of the body, and afterwards we fill it with fugitive material in order to ensure that the structural integrity of the microchannels are fine during lamination and firing. The pinholes are filled with silver paste, and afterwards the entire device is laminated once more before finally being fired for sintering. So for the design process, it started with material characterization to ensure that all of the components would be compatible. We then looked at thermal management considerations to ensure that, which resulted in a pin-based platform for the heating elements to sit upon. Fluid analysis was conducted for testing procedures as well as the equipment needed for testing. For design alternatives, the majority of the design alternatives were looked at for the configuration of the microchannels themselves, as well as the different layouts of the silver pins. Ultimately, we decided to go for simpler single-channel flow, which has already been proven with LTC technology. That will be implemented with an array of silver pins, and silver was chosen due to its naturally high thermal conductivity. For the materials, extensive research and experimentation was used to finalize a list of materials for the manufacturing process. As this was a manufacturing process based on LTCC, the ceramic will be the only material that remains once firing has occurred. Upon further research, we decided to introduce a glass powder to further promote sintering and achieve a uniform, hermetically sealed structure. Polyvinyl was used as a binding agent. The fish oil was used to promote even distribution of the fish oil of the binding agent, and the plasticizer gives the tape its ductility, which reduces the likelihood of brittle failure. Fusion of materials such as paraffin is used to promote structural integrity during lamination and firing. So these are the costs incurred during the life of the project. The majority of the cost was due to the purchase of DuPont's tape. After that is the silver paste used for the pins, and the rest of the costs are due to testing equipment, materials, and the operational fees for the different machines used. This is the firing profile used for the final assembly of the regular device. It is based on the same LTCC profile, firing profile used for DuPont's tapes. Each of these plateaus seen here are different sections where different components of the tape is burnt out. So once the solvent, the binder, and the fugitive materials are burnt out, sintering occurs at the midway process during the peak temperatures. Then the temperatures are ramped down at a steady process to allow for creep. Creep is an important step because it allows for the relief of thermal stresses at the interfaces when you're firing metals such as silver at 40 to 60% of the melting temperature. We then conducted a Vickers hardness test using 3 different samples. Each of the samples were fired with different glass powders. The most consistent best results were that of the ASF 1109. The other 2 samples had high deviation, which likely resulted from the microstructure and interaction of the silver pins and the regular particles. The 1109 sample is achieved the hardness comparable to aluminum, which was our baseline target. So a scanning electron microscope was used. Here you can see the clear distinction between the 3 samples. The 1109 has a uniform, smooth surface, which is important in providing hermeticity. Hermeticity means that the fluids won't permeate through the allergen, which is important for this kind of device. The other 2 samples are obviously uneven and jagged, which would be also likely reason for the deviations in previous slide. And finally, our design concept was consists of a square 60 millimeter body with a 30 millimeter wide, 1 millimeter thick cavity for fluid flow, and an 11 by 11 array of pins which extend through the top surface of the device through the microchannels. The array was served as a platform for the heated element to sit upon. And I'll give it over to Jonathan to go over the actual performance and testing results that we obtained.
So here we have the first prototype in its engineering drawing. Top section is it actually compiled together how it will look when it's completed, and the bottom section is an exploded view, where we have the working fluid in blue, the ceramic body in beige, and the pin array in silver, and the resistive heating element in green. Next slide, please. So when we manufactured this one, it worked perfectly well, except for in the firing. During the firing, we had a fracture and collapsed channel. All the cracks that you see here, the only ones that actually happened during firing were the ones in the center. The rest of them happened during post-processing, trying to figure out what happened. So we went on to a second prototype. On this prototype, we took that one channel, split it into 5 subsections, with 2 channels being support sections. Therefore, we could ensure that there wouldn't be any collapse of the channel, and we could find out if the fracture that happened in the pin array section was due to the pins or due to the actual device, and the LTCC being in that section with such a large channel. So here we only have 1 row, and the pitch was doubled. Next slide, please. So over here, I'll pass it around. We have the prototype number 2 that actually worked nicely. Here you are. In this prototype, we have a flatbed of silver on top to ensure that proper conduction of the heat over the entire surface, and the pins are through it, as you'll see. There was no failure, and we had proper channels that were created. Next slide, please. Over here, the actual construction of this was constructed in LTCC and in Regolith. This is the DuPont's LTCC green tape. And it's called green before it's fired. And this is our Regolith green tape. Yes. So with those tapes, we cut them to the proper size. We would peel them off of the mylar on the back and stack them into 1 millimeter and 2 millimeter thick stacks. That's 10 and 20 different layers of them in order to do that. Once we did that, we pressed it, as was said before, and we routed out the channels. We cut the LDPE, the polyethylene, to fit in those channels, stack the top and bottom together, the 1 millimeter thick and the 2 millimeter thick stacks. And then we grouted vias through the center in the design that we want. After doing that, we filled it with the silver that we want. During the silver filling process, we had to optimize which silver we wanted. So we have 3 different silvers here, trying to figure out actually which one would work best. And we have it over here done in regolith to see which one would work best. It ended up being that it was the same silver that worked the best out of all of our choices. And so we went ahead with that one. And then we fired them as the firing profile that we had done earlier. We proceeded with a Fpm design analysis. We used a 150 Newton force, and we determined what the safety factor, what the maximal stress would be that a device can withstand before failure. We then did a conjugate heat transfer analysis using COMSOL, and that would determine the maximum heat in the temperature of the device, and it would determine maximum temperature of the working fluid, which is water. We needed to avoid boiling, and the pressure drop across the device. So here we have the first stress analysis, which was fixed on the top, force on the bottom, so it's vertical. The displacement and stress shows that it's most in the channels. That's what we would expect. So this is proper. This next one, same concept, except that the stress is being applied on the external part of the channels, all the way across the face. And here, same sort of situation. Next slide. And then for here, it's compression instead of tension. And in the displacement, you can also see that it's the most amount of displacement in the channels, which is what we expect. On this analysis, you can see the minimum factor of safety is over 100 for each one. So this device should withstand all the forces that we expect that it will encounter. For the conjugate heat transfer analysis, on the left you have the top side view, and on the right the bottom side view. This is our heat map through the simulation. You see that the most amount of heat on the bottom side is where we have the support structures. So in the future we would want to widen those channels and make it so that all that heat would be dissipated. Here with the thermal fluid analysis, we have streamline velocity. On the top side on the left, you can see that the fluid is actually flowing much faster than it is on the right, and that's expected because hotter fluid will flow faster. On this, we'll have a heat source of 33.5 watts per centimeter squared, and an inlet temperature of 21.85 degrees Celsius, inlet velocity of 5 meters per second, and no pressure with no backflow on the outlet. That's gauge pressure, not absolute. And that should give us a delta T around 9.23 degrees Celsius. And maximum temperature in the fluid of 96.84 C, which is below boiling, so we avoided that.
All right, so now after the device has been constructed and analyzed, we needed to test it. In order to test it, we had to have guidelines, and for those guidelines, we used industry standards. The one that was particularly applicable to this project was the MIL Standard 883. Essentially, what this does, among other things, is it tests for thermal impedance of boards. So, with that being said, we have to mention the devices needed for this testing were beyond the means of anyone in this group as well as the department. So what we had to do is we had to adapt the testing to best suit our abilities and make it as accurate as possible. The other standard that we came across is the ANSI AHRI 400. And what this standard is for liquid-to-liquid heat exchangers. It could be adapted for a single-phase heat exchanger, which is what we have, but it was particularly for pressure losses associated with the device. So essentially what it tells you is that if a manufacturer prescribes a pressure loss, the customer can expect to see within 10% of the prescribed pressure loss. As we did not use pressure losses or test for it in this project, we didn't actually use this standard, but it is applicable. So this was the test that we had for thermal impedance. This is the MIL Standard 883. Essentially what you see here is a K-type thermocouple embedded in an interface between the resistive heater, which is on the back side, which is connected to a power source supplying the power to heat the actual element. In the interface, we had a silver compound that was a thermal grease that allowed for decent conduction between the resistive heater and the board. And as you see, this board is the regolith board. We also use the DuPont 951 board as well, same configuration. And essentially what we did is we had a grid on this that was 5 by 8. So we had testing points at 40 different locations within that silver area. And then we took and averaged those temperatures on the backside of the board and used the equation based on the mill standard, which you'll see right here, which is the difference between the junction reference, which is the embedded thermocouple, and the average case temperature, which are the 40 points averaged. This is per unit of power of watt, or per unit of power. So with that being said, we found the DuPont 951 produced a thermal impedance of 4.06 degrees Celsius per watt with a standard deviation of about 0.5. The regolith had a slightly higher thermal impedance, which was 5.37 degrees Celsius per watt, with a lower standard deviation of 0.4648. For comparison, these are typical industry standards for boards, and as you can see, our devices, both of them, perform better than typical FR4 boards with different weights of copper, which each of those is 1 ounce, 2 ounce, and 3 ounce, are ounces per square foot of board. And then, with that being said, it came close to an MCPCB, which is solely a metal board, which says that our device actually performed very well. These are the 4 different tests that we had. It's 120 different data points for each material. And as you can see, for the DuPont 951, the last 3 had a very low standard deviation, and the opposite is true for the regolith. The first 3 had a low standard deviation. The next set of testing we did was the heat dissipation using a fluid medium. And yes, he's passing around the devices that we used for this test. It essentially had the same setup. There was no embedded thermocouple between the interface, but the resistive heater was placed on top of it. A thermocouple was measuring the inlet temperature, and then 3 thermocouples were measuring the outlet temperatures. The correlation for heat dissipation and the amount of power that's being convected out of the system is based on the equation with the mass flow rate, the fluid property, specific heat at constant pressure, and the temperature difference between the inlet and the outlet. So these are the testing that we did. We had a power input from our generator that was 11.25 watts, and as you can see, the 3 tests came very close to that. The first one is somewhat of an anomaly because it has higher convecting power than was actually being put into the system. You see the second 2 were what was to be expected, especially considering that you will lose some of the heat through convection of the actual board itself and not through convection through the water. And we would have done more tests, but unfortunately the water started to creep up onto the resistive heater and water and electricity, and we decided. All right, and the last thing that we tested was the reliability of the regular channel that we made. So what we did is we did this through visual inspection. We took and ran that device right there with a gravity pump for a period of 30 minutes. And what we did is we watched for delamination of the individual layers, as well as accumulation in the reservoir of individual particles that would hint at erosion of the interior channel. With that being said, for the 30-minute period, we found no delamination, nor did we find any particles within the reservoir. So with all this being said, the awareness this brought all of us was primarily the exchange of information. We realized we wanted a project that had universal implications, so we had to have it available to other people that didn't necessarily speak English. So with that being said, we produced a process manual in both in English, Spanish, and French, so that way globally people could use our process and make the same material. Another thing that I brought to our attention was the awareness, especially in materials that go into manufacturing tape. With that being said, all of us had to go through special training with AMRI, the Applied Materials Research Institute downstairs, for the safe handling, use, and disposal of these materials, particularly the binders and the solvents, as those were very nasty stuff. And finally, it highlighted the cost of development of engineering products. And this is especially true if you're going to use engineering materials, which as he showed you with the pie chart, you can see the standard DuPont 951, which is engineering material, was the bulk of our cost in the project. And on top of that, we couldn't procure the needed devices for the testing because they were so expensive. So we got to see how expensive it is to be an engineer. And on an individual level, it taught us how to work in a design team. This is absolutely important if you want to be involved in a large organization and industry. Beyond that, we also learned about developing materials, analyzing systems, prototyping, and testing these devices. Further, it taught us how to take a concept and actually produce a device with it. And finally, it really gave us an opportunity to take all the information we've learned over the last few years and apply it to a project. So the conclusion is we successfully produced an LTC heat dissipation device using convective heat transfer. It was characterized and a basis for performance was established. A regolith tape channel was produced and tested successfully. And on top of that, the thermal behavior of the DuPont 951 as well as the regolith board was characterized using thermal impedance. Beyond that, construction of a regolith-based device for heat exchanging using the fluid medium is left to be for the future, as well as using a fin design instead of a pin design, allowing overall a larger area of convecting surface. So we would like to thank the following people, especially true for all the people that are associated with Amory. They helped us out a lot. So thank you. Questions?
Any of your devices going up today? They're launching,
No, not with launch.
not with the launch today.
No, there's a launch today.
That's a launch for the deep
Orion.
space,
Can you
Orion.
come on that
Okay.
side? Yeah, you can stand with them.
All right.
Yeah, they had some delays that, according to the news, that there was a boat in the area that wasn't supposed to be there, that they had to clear him out. So,
No, when I was driving up here, they were just saying that they moved up the lunch before, like about 11 o'clock, and moved up, I think it's like about this time. Hopefully
Okay.
everything checks out, so hopefully they went up.
Very cool.
I have a good question. Out of all your projects, what did you find is more challenging between managing the project, doing the testing, and manufacturing? What would you say was your most challenging aspect of the whole project?
For me, and I think I can speak for all of us, it was developing the tape. That, I mean, we're not materials engineers, we're mechanical engineers, and that was a very materials-based process. But with that being said, that was also the most rewarding part of the project, because it really got us out of our comfort zone and forced us to produce something that we're not familiar with. So,
Yeah, cool.
Any other comments? Yes.
Yeah, I have 3 questions, one for each of you. So let me start. First question I have is, and fellow in the middle, I'd like to ask this question. Let me put the glasses on so I can read it. I did read your report, by the way. Where in the experimental work did you determine the particle size? And you made a statement about the fact that the goal of the project was to have minimal effort in space. How are you going to achieve that with retrograde material?
Yes, as far as determining the actual particle size, during the initial procedure for formalizing the tape casting process, we milled the regolith simulant, and we used a fine grain gauge to actually get a average particle size. I think we achieved was less than 10 microns. 3.
that was the D50.
Say again?
The D50 was 3 microns.
The average
3 microns.
Yeah.
And as far as our initial, as far as making it easy to reproduce, we tried to use equipment and processes that we thought would be easier to get into space. As far as using a manual heated press, physically casting the tape with a doctor blade instead of using a large device or equipment, and ball milling, which could theoretically be powered by, say, a bicycle, as far as getting it to generate the necessary revolutions. Those were all the things that we considered as far as using the actual equipment. We didn't want to do anything that was too expensive or too unwieldy for the average person. It's not likely to be used across the globe in, like, say, less developed nations, because it does require a certain amount of resources to obtain everything, but it could theoretically be used on a lunar site with the right materials and equipment.
Okay, great. Your turn. Okay. Question I have for you is, could you put up the firing cycle? There we go. Okay. Did you do any work to determine how large those steps need to be? Because there's a lot of money
In terms of ramp rate?
Ramp rate and duration.
So ramp rate was decided by the inks, the silver ink that we use, or silver paste, that decided, they said, DuPont said that, sorry, Harass said that it was 5 degrees C per minute. So that decided
That
that.
dictated the ramps,
Yeah.
okay?
So that was the slowest of all of our needs, so yeah.
And what about the burnout durations?
Burnout durations, that was through research. We figured it out and through trial.
Okay, was there a difference between the low temperature co-fired and the retrograde?
No. When we actually, well, we have the samples here. You can see that in this one or the other one.
Well, I mean, you showed me a cracked one,
Oh, so
and so that would suggest that the cycle might not have been correct.
so that one was with a different cycle. That one was with a
How did you
faster
change the
cycle.
cycle?
We were doing 10 degrees C per minute, and we didn't have these two sections here. We were just dropping straight down, so we didn't have anything to relieve the stress.
Okay, great. Your turn. Okay, I didn't see a retrolith with multi-layered, with the water channels, with the pins. Did you actually create one?
No, that is why we stated in the last slide for the conclusion, that is left for the future. That's something that still has to be produced as well as a fin-based design.
And why didn't that get done?
It
Because
was
I think that would have been your goal, right?
Yeah, it was definitely attempted.
The machine.
Well, yeah, we had problems initially with actually getting it to laminate properly and cutting out the channels and everything. And we finally did get it to work where everything was stacked appropriately and was ready to be put together. And our routing machine upstairs decided to go on the fritz.
Okay. And so that's also the reason why you didn't have thermal heat dissipation tests for retrolith?
Well,
We did that.
we-
Oh, yeah,
No,
yeah,
no,
for
you
the
had it
convective
for the
process.
LCC.
Yeah.
Yeah, we did not do that because we didn't have the device to test it with.
Okay, thank you. Mike?
Anybody else?
One general question. So I think you guys got a pretty good insight into a number of the things that I've seen, at least in the industry in the last couple of years here, from quality control to manufacturing processes, pretty much through the gauntlet. What would you see as the biggest cost benefit versus risk, if you will, for if you were going to implement this into space? Because all of these processes take equipment, and you said your ultimate goal is ultimately to lessen payload as much as possible. So what do you see as the long-term ramifications of maybe the number of components that would have to be replaced versus what it would take to actually manufacture it?
Okay, so you're asking what we would reduce as far as devices being sent with the astronauts?
Versus developed in space, yes.
Okay, I mean, to be completely honest, I don't think we ever put it on paper with, in a NASA mission, this many pieces of this many electronic components go into space, vice versa, what could be produced with ceramic manufacturing. But with that being said, we produced a regolith-based device that was for heat dissipation capabilities. But I mean, when we did the literature survey, we found many applications. One of them was building actual houses. You wouldn't need to send a structure into space. You could actually build I don't want to say house, but a facility on the moon solely out of lunar regolith.
I also wanted to add that initially we were considering possibly creating a regolith ink to be used with 3D printers. So that would have been a way to remove the amount of materials and equipment needed. So you would just have a 3D printing machine and the ink itself.